The topic, as announced in your note, it is environmental degradation and climate change. Now, I will mainly confine in this initial discussion on the scientific aspects of the climate change, even though the major controversy now is not so much on the science, but on the politics related to the climate change. And about environmental degradation, I shall touch upon the environmental effects of the climate change, but environmental degradation has many other issues which I shall not discuss in this discussion. The climate change, I will, why isn't it? I will discuss mainly 4 questions related to the climate change. Firstly, is there global warming? If yes, then is the warming natural or anthropogenic? What is the impact of the climate change? This is where the environmental aspects will come. And finally, can we predict and thereby mitigate also the effects of the future climate change? Now, regarding the first question, in the 19th century and the first half of the 20th century, the given scientific wisdom was that the climate is a stable phenomenon and there is not likely to be great change in the climate. It is only in the second half of this second century, this idea of climate change took the center stage of scientific discussion. And there were, in the initial stages, there were some scientists or many scientists who were propagating the idea that the Earth is on this way to climate change. And there were equally others, not so much from the scientists, but mainly from the politicians and from the corporate houses, particularly the oil lobby, who vehemently denied the reality of the climate change. And then there was controversy also whether the climate change is a natural, even if we accept that there is climate change, whether man has to do anything with it or whether it is natural phenomenon. So these 2 questions will start together. About the first point, if we start with the first point, the main problem with to sell the idea of climate change is that there is a great, firstly, let us see what climate is. Climate is primarily controlled by the certain parameters in the atmosphere like temperature, humidity, wind speed, etc., and many similar other things. So that constitutes the climate. We use 2 terms here, weather and climate. These are scientifically well-defined terms. Weather refers to the present state of the atmosphere, its temperature, humidity, wind speeds, etc. And it is generally averaged out over the day or over the week. And climate is the average weather over a long period of time. And traditionally, this period of time is over a period of 30 years. Climate is the average weather over a long period of many years. And traditionally, this over a period of 30 years. And this 30-year period is arbitrarily chosen. We can choose it as 1950 to 1980 or 1920 to 1950, like that. Now, the question about the climate change is, the controversy started in the initial stage because there is a lot of variability in weather. We have variation of weather during a day from one place to another. So in space and time, there is a variation of weather, and there is a variation of weather also over long periods of time. For example, we have summer, autumn, winter, like that. That is a variation of weather over one period of time. And these seasons come in a cyclic way. So we find that the winter of one year is maybe milder or more cold than winter of another year. So this is a sort of a natural variability of both weather as well as climate. And to find out whether there is any, any change that we perceive, whether it is a natural variation or whether, natural perturbation, or whether there is any directed change of the climate. For that, on the Earth, which are distributed all over the globe, you can see that in this diagram, that there are some stations which are very old. The oldest one is about 150 years or nearly 170 years old now. And then there are some stations which were established later. So what they do, how do we specify the average temperature of the Earth? Because the temperature varies from one point to another, and also from one day to another. So how do we define an annual average temperature of the Earth? So what the scientists do is that in every day, the temperature is measured at the weather stations, and the average is taken of the entire day. And then that average temperature is compared with the usual temperature at that point. By usual, we mean that I mentioned about arbitrarily chosen 30-year interval. So the average temperature during that 30 years interval on that day at that station is the average temperature of the reference period. So the temperature difference of a particular day on and with the reference temperature on that same day, on the same date, that is the temperature anomaly at that station for that particular date. So if it is positive, that on that date, it is hotter than the usual temperature. If it is negative, then it is colder than the usual temperature. And then at that station, these average anomalies for that one particular day is measured on every day of the year. And then the average for a month is calculated. And from the monthly averages, the yearly average is calculated. And this same exercise is carried out over the thousands of the weather stations distributed all over the globe. And then an average is calculated, for the global average is calculated, and very elaborate statistical methods are employed to arrive at that global average from these thousands of stations measured over 365 days of a year. So after that calculation, we get an anomaly of which is the annual anomaly of the globe in a particular year compared to the reference period. And then that is plotted in a time series. And then we see that whether with the passage of years, the temperature is increasing or decreasing. So this is, we have instrumental records of temperature from about 1850. So from 1850 to, so this is for the, from 1850 to 2020. And this is, the reference period is chosen here as 50 years from 1850 to 1900. This reference is chosen so that to see the 1850 to 1900, that is the peak period of industrial revolution. So with reference to the temperature condition during the industrial revolution and today, so how much, whether there is any systematic rise in temperature. So you can see that there is the land average and ocean average. And you can see the land average temperature has increased by almost 2 degrees, 1.96, and ocean temperature and is about 0.83. And that it has really warmed, the temperature has gone up. It is also indicated by the fact that the last 6 years are the warmest 6 years during this entire period of 1850 to 2020. So the warmest 6 years are the last 6 years. So this is how the scientists established that the average global temperature is really increasing with passage of time since the time of the Industrial Revolution. Now, the question naturally arises, what about prior to the Industrial Revolution? Was there the same conditions like that? So has the temperature increased with reference to the period before the Industrial Revolution? So before 1850, we don't have instrumental records of the temperature, but we can deduce the temperature from some rock records or soil records, some from tree rings. We can estimate the temperature. And from that estimates combined with this, we can see the, one point I forgot, that the global average temperature, I said that it is 1.96 degrees centigrade for the Earth as a whole, average warming. But this warming is not uniformly distributed at every point of the Earth. This map shows that which part of the Earth is getting more warm and which part is getting less warm. So you can see that the near the North Pole, the Arctic area, northern part of Siberia, this is the part which is getting warmest now, which has got great implications I shall discuss afterwards. And Europe also is getting very warm. India, we are in a better position. We are not so warm like in many other parts of the world. And there are some oceanic areas which are cooler than the reference period. So that is also significant. So this is the cool area, this is the cool area, this is the cool area, and this is the hottest part of the globe. So, as I was mentioning, over the past 2000 years, if you see, this is the temperature. The bold curve here is the average temperature, and the gray band is the variation from the average. It's a 2 sigma variation, just to give you an idea that what is the variability of the temperature from the average. You can see that for the last 2000 years, the trend was in the up to 1000 AD, from 1 AD up to 1000 AD, the temperature was varying, but the average was more or less horizontal. That means the temperature was more or less constant. Then it dipped downwards. So the average temperature became less, it was cool, and this is known as the mini ice age. So, and this part is not a global phenomenon. The effect of this mini ice age is found mostly in Europe. It's also because partly this is a data deficiency, because most of the data have come from the European part. There is very little work done in other parts of the world from these rocks. So this effect of the mini ice age is not very prominent in India, maybe because of we don't have enough data from India. And then from somewhere near 1850, this part, the temperature started rising up. And rising up at a very steep rate, you can see that it was a very slow cooling here. And then from there, it is rising up in a very, very, very steeply rate. So this warming is, this is the temperature now, temperature anomaly now, almost 1 degree centigrade compared to this industry 1850 to 2020 years. So it is 1 degree temperature. So this is the warmest period, and this warming is unprecedented in more than 2000 years. And if you see the 2-3 centuries, then this 2-3 centuries, this part is again, there is some warming here, this very outlying values, which is the warm part here. But this centuries, if you take the 2 centuries, this 19th century and 20th centuries, they're warmer than the previous, not only 2000 years, but 100,000 years. If we go back further down to earlier period, then we come to the period of the ice ages. We have cyclical glacial age and interglacial age, warm and relatively less warm, overall cool, but relatively more warm and relatively less warm. And the data have come from ice cores in the Antarctic. This is a Russian station, Vostok, and this is a European station. And you can see it in 2 different places in the Antarctic ice sheet. And you can see that the nature of the curve is almost identical. So this is the interglacial period. This is the glacial period. And this is the temperature scale here. So you can see that the temperature difference between the peak coolest part and the warmest part is about, the coolest part and this is the warmest part. The difference is about 6 degrees. But overall, you can see if you take the average of this toothed curve, this is more or less horizontal. And then it started rising, and in the end, it rose, it has started rising, and it shows that hockey stick curve which I showed earlier. And so this is the glacial, interglacial age. So climate change is not only in the recent time, but there was climate change earlier also. And if we go still back up to 65 million years, Why have you taken 65 million years? Because 65 million years is a major geological event which is marked by a giant meteorite impact, which brought about great changes all over the globe and the extinction of the dinosaurs. So there is a great biological change and great physical change. So you see here, this curve, here, the temperature here is about highest temperature here, average temperature, average global temperature is about 12 degrees higher than today's average temperature. So it was like a hothouse. It's much hotter than today's Earth. And then it started cooling from 52 million years. And it started, the Antarctic glaciation started from this about 32 million years ago. Then there's this peak thawing, Antarctic thawing, and then again Antarctic cooling. And then we come to this part, which is the graph which I showed you earlier, where we have this rapid glacial cycles. And finally, afterwards, this today's temperature, which is somewhere here, somewhere in this region. So previously, the highest temperature was about 12 degrees more than the today's temperature. So climate change is a reality. It happened in the past, and during the last 150 years, or 1850 to 220, about 170 years, the global temperature land temperature has increased by about 2 degrees, and the ocean temperature has increased by about 8 degrees. This is based not on any opinion or fanciful ideas. This is based on actual measured hard data and statistical calculations. So scientifically, no one can now deny the reality of climate change, and particularly that since the beginning of the Industrial Revolution, the temperature is steadily rising very steeply during the last 50, 70 years, compared to whatever temperature change it took place early. So now the next question is, what causes the climate change? Now, obviously, the climate change which took place 65 million years ago, or the climate change which took place about 10 million years ago, those climate changes must be due to some natural causes, because human beings were not present there. So there is no question of any human-induced or anthropogenic climate change. The question comes when from 1850 to 170, how much of this climate change is due to natural cause and how much it is due to human activity? Because we have actively tempered or actively modified our activity, human activity is actively modified the parameters or the conditions, mainly the chemical characters and consequently the physical characters also of the atmosphere. So how much of the change is due to natural causes and how much of the change is due to human causes, that is a valid question for the scientists to be tackled scientifically. So to see that, let us understand the basics of the what controls the climate. The climate is controlled by the energetics in the atmosphere. And the energetics in the atmosphere, the energy is primarily comes from the sun. And if we have an equilibrium condition, by equilibrium condition, it means that the temperature may vary, but the average temperature over a period of time remains the same. In that type of condition, we call it an equilibrium condition. Then in the equilibrium condition, whatever radiation the Earth and the atmosphere receives, the solid Earth and the atmosphere receives, and whatever radiation goes out from the Earth and the atmosphere to the outer space, balance each other. So when they are balanced, then the atmosphere is in a stable condition. The temperature has some sort of a stability with minor statistical variations. Now, how is this incoming energy coming from the sun, how it is distributed in the atmosphere? So roughly about 341 watts per meter square. Watts per meter square is the energy which is received from the sun. A small part of the energy is reflected from the clouds, and a still smaller part is reflected from the surface of the Earth and goes out to the atmosphere. So these reflected back energy does not play any role in controlling the energetics of the atmosphere. A small part of the energy is absorbed by the atmosphere, and a larger, very big part is absorbed by the land, by the surface of the Earth. So this is about the incoming energy. And what about the outgoing energy? Now this atmosphere, this energy received by the land, received from the sun, this heats up the Earth, and as a result, the Earth emits the radiation back to the atmosphere. So it comes from the hot air moving upwards. It comes from the evapotranspiration process, evaporation from the soil, and the transpiration from the plants, so that some energy is transmitted to the atmosphere and absorbed there. A large part of energy is the surface is emitted from the surface. It is absorbed by the solar energy is absorbed by the Earth, and this energy which is emitted by the Earth, a very small portion of it goes back to the directly goes back to the outer space. The major part of it is absorbed in the atmosphere by the presence of some gases which are known as the greenhouse gases. So they absorb the radiation, infrared radiation, which is emitted by the Earth, and the atmosphere is absorbed, and that energy is expressed as the increasing temperature of the atmosphere. And the atmosphere itself emits the energy back. Part of it is emitted to the surface, warming up the atmosphere, or warming up the land, and part of it, the atmosphere emits back to the radius. So that whatever 341, and this is going out directly reflected back from this cloud and the surface, and this is going to the atmosphere, going to the space from the atmosphere. So this 235, 187 is together equal to 340. So whatever comes in, the same thing goes out. Similarly, the Earth's surface also, it absorbs the energy from the sun directly. it absorbs the energy from the atmosphere, and so this total energy is radiated back by the Earth. 350 goes to the atmosphere, and then this 2478, 350, and a part goes directly to the outer space. This together is the 390. For about this 324 and 168, this is the same as the summation of this. So all this is an equilibrium condition. Whatever the Earth receives, it emits back. Whatever the Earth and the atmosphere together receives, it goes back. And the temperature of the atmosphere increases because of the presence of some gases in it, which is called the greenhouse gases. The basic physics of the process is clear. So this part, let's go back. So this is the equilibrium condition. So whenever this equilibrium is disturbed, that means if there is more energy coming to the atmosphere than emitted back, that is the disturbance of the atmosphere, and the temperature increases. And if it is the other way, that more energy is emitted back to the space and less energy is received from the sun, so that leads to a cooling of the atmosphere. So more energy is emitted, it's cooling, and more energy is absorbed, that leads to heating. And whatever energy, this is the top of the atmosphere, which is called the tropopause, and whatever energy comes, extra energy from the equilibrium condition comes inside or outside, that controls the change in the state of the atmosphere. And this energy coming in or going out, that is known as, in scientific parlance, as the radiative forcing. So the radiative forcing is the extra energy coming in or coming out at the tropopause. So what causes the climate change? Obviously, one way more energy or less energy can come to the atmosphere because of the solar changes in the solar irradiance. If the sun gets brighter or the sun gets dimmer, there will be more energy or less energy. And then the presence of the greenhouse gases, which absorb the gases in the atmosphere, which absorb the energy. If there is less of greenhouse gas, it will absorb less energy. If there is more of greenhouse gas, it will absorb more energy. And then there is the surface albedo. A part of we said that a part of the energy is reflected directly back to the space without being absorbed. So that is called the albedo. So if the albedo is greater, that means more energy is reflected back. If albedo is less, then more energy is absorbed by the surface. So for example, if there is ice on the surface, there will be more energy will be reflected back. If the ice is melted to form a water body, more energy will be absorbed by the water body. So this is surface albedo is a factor. Then there is aerosol. These are tiny liquid droplets or gaseous droplets which exist in the atmosphere, which are emitted in the atmosphere. So they are also they can be positive forcing or negative forcing. Remember that positive forcing leads to warming of the climate and negative forcing leads to cooling of the climate. The basic physics of the the most of the climate change is the discussion is focused on the role of the greenhouse gases, because we shall show later that the greenhouse gases has the largest contribution to the changes in the atmospheric temperature. So most of my discussions will be with reference to the greenhouse gases. Now, the basic physics of the absorption of energy was in the greenhouse gases was worked out in the 19th century itself by two pioneers, Joseph Fourier and John Tyndall. They showed that some molecules, the molecules of some gases, like water vapor, like carbon dioxide, they absorb the infrared energy when it passes through them. So this is very clearly seen in the absorption spectra of those molecules. But their interest in the absorption of the carbon dioxide, absorption by carbon dioxide of the infrared energy was not so much about the global warming, but at that time, the presence of the ice ages were being newly discovered. So they were more interested in finding out what caused the formation of the ice ages, that is the cooling of the earth. That was their main interest. They were not so much interested about the warming, because the warming was not very visible in those days, if you remember that curve. In the 1850s, that there was average temperature was the same, more or less the same for the past thousands of years. So this is shown in this thing. Now the entire problem arises because the energy, the spectrum of the energy that is received from the sun and the spectrum that is emitted by the earth, they are at different wavelengths. The spectrum of the sun, it is emitted at a temperature of about 5,000 to 6,000 degrees centigrade. And this is the profile, spectral profile. So most of this energy comes in the visible range. A little bit of it comes in the infrared range. Whereas the energy that is emitted by the earth is at a much lower temperature. It is at a temperature of about, say, average temperature of the earth is about 14 to 15 degrees centigrade. And this is the spectral profile of the earth. And this is the possible variation. So you can see that this most of the thing is in the infrared region. And these are the absorption spectra of the different gases which are present in the atmosphere. Nitrogen is a major component of the atmosphere. Nitrogen does not absorb the infrared energy. Oxygen and ozone, they absorb a very little part of the infrared energy, and these are the wavelengths which are absorbed. So this is the water vapor, which absorbs all the energy in this wavelength, and so there are several wavelengths in which the water vapor absorbs the energy. Carbon dioxide absorbs the energy in this wavelength and several small other wavelengths. And oxygen and ozone, very little in this wavelength. Methane is also a greenhouse gas. Nitrous oxide is also a greenhouse gas. We'll leave aside the Rayleigh scattering problem now. You can see now that most of the infrared energy which goes out to the outer space is at this wavelength. The rest is all absorbed in the atmosphere. most of it is in this bit of wavelength and a little bit here. So this absorption of this wavelength causes the warming of the Earth. If there was no atmosphere, the surface temperature of the Earth will be at about -5 or -6 degrees centigrade. It is because of the presence of the atmosphere that the Earth is at an average temperature of about 13-14 degrees centigrade, which is suitable for the flourishing of life on the Earth. So this is the, remember these points, the wavelength in which the absorption bands for water vapor and for carbon dioxide will, because this has got some important role to play. And this absorption phenomenon of the carbon dioxide and water vapor, this was known in the 19th century from the works of Fourier and Tyndall. In the later part of the 19th century, a Swedish physical chemist, Arrhenius, he was interested in this absorption by carbon dioxide, and he realized that since the Industrial Revolution, industrial activity from the burning of coal has emitted a lot of carbon dioxide, which has gone to the atmosphere. And since carbon dioxide goes to the atmosphere, and since carbon dioxide absorbs the infrared energy emitted by the Earth, he was wondering whether the presence of this carbon dioxide would lead to warming. So he made some calculations, and he said that his calculation showed that the doubling of the carbon dioxide would increase the temperature by about 5 to 6 degrees. But this idea did not find the acceptance by the major part of the scientific community, because in those days, in the later part of the 19th century, the idea, you remember that the metaphysical way of thinking, philosophy was dominant then. That permeated in this field also. The idea was that the Earth's climate is something stable. It does not change very much. It varies from year to year, but within a certain range. It cannot have a permanent change or a permanent change of the climate from one state to another. That was not very much accepted in those days philosophically, and they presented some scientific arguments also to support that. The arguments were that the carbon dioxide, even if it is emitted into the atmosphere, there is a large volume of water in the oceans, and carbon dioxide is very soluble in the water. So whatever extra carbon dioxide is emitted to the atmosphere, eventually they will be all dissolved in the ocean. So the atmosphere will not have any carbon dioxide. That was one argument. So even if we emit the carbon dioxide, that will not stay in the atmosphere for very long. It will all go back to the ocean. And secondly, they said that the absorption bands of carbon dioxide and the absorption band of water, they are more or less overlapping, so that whatever infrared radiation is emitted by the Earth, whatever is absorbed by the water, because the carbon dioxide absorption band is on the same wavelength, there will not be any additional contribution from carbon dioxide. If you see that this part is overlaps with the carbon dioxide, with water. This part of carbon dioxide is overlapping with the, so the addition of carbon dioxide will not have any effect. However, later what proved both these ideas to be wrong. We shall come into that. In 1938, Arrhenius's idea was revived by Callender, a man called Guy Callender. He measured the carbon dioxide in the atmosphere from the Industrial Revolution period and in the 1930s period. And there are very crude measurements in those days. Not very precise measurements could be made in those days, but there was certain increase. He found some certain increase. And then he compared the temperatures, the surface temperatures in the industrial period, revolution period, and the surface temperature in the 1930s. And he said that there is a slight increase in the average temperature. So he said that that indicates that the carbon dioxide is increasing. But this, he faced very strong opposition from the scientific community because they said that the carbon dioxide measurements are imprecise, so they cannot be relied upon. And similarly, the temperature measurements during the Industrial Revolution period also was not very strong. But then, controversies went on. But Callender was a very courageous, tenacious person, and he kept the idea of carbon dioxide-induced warming alive for many years, till going into the 1960s. And then 1960, David Keeling from the United States, he said that let us go make some accurate measurements in an area where there is not much human activity and see whether the atmospheric carbon dioxide is increasing or not. And over a period of decades, he patiently measured the carbon dioxide in a station at Mauna Loa in Hawaii. In that Mauna Loa, there is very little human activity. So he could went on measuring the carbon dioxide and conclusively proved that the concentration of carbon dioxide was increasing from year to year and produced the famous curves known as the Keeling curves. So this is from 1960s, he started measuring. In every year, there is a high and there is a low. So that's an annual cycle of carbon dioxide. So it is, the curve is a toothed curve, a high point and a low point, which is seasonal variation. But with that seasonal variation, every year you can see that it is going up. So, and it is this Mauna Loa station is still going on measuring even now. So this, from it started, from the Industrial Revolution, it was about 275. So in 2000, it was 360, and today in 2019 or 20, it has exceeded 400. So the carbon dioxide which we have emitted, a large part of it is staying in the atmosphere, and the concentration of carbon dioxide is increasing. So there is a valid reason to correlate the temperature increase which is proved by the global measurement of average temperatures from 1850 to 2019 and the measurement of carbon dioxide. They correspond. So there is a correlation between these two. And so there is a reasonable to ascribe the increase in temperature to the increase in concentration of the carbon dioxide. And they said that let us see, compare with the past also, whether that this correlation remains, then that would strengthen the argument that whatever warming we are seeing now is due to increase in concentration of carbon dioxide. So this is that during the last 2000 years. So you can see that this was a more or less stable period with a slight cooling. And this is the mini ice age, and then increase in temperature. You see all the three greenhouse gases, they show the identical hockey stick curve. During this entire period up to 1850, they're more or less horizontal with a slight dip here, which corresponds to the mini ice age. That means it gets slightly less, and then it rises very steeply when the temperature also rises very steeply. If we go further back in the period of the ice ages, do we find the same thing? Yes, indeed. This is, you see, during the ice age, this is the temperature variation. This is the glacial period, ice age period. This is the interglacial period. You see the carbon dioxide and methane curves. This is the methane curve. They exactly mimic the temperature curve. And this carbon dioxide and methane is measured from the air bubbles incorporated within the ice core. So you date the ice core, say dating is about, say, 300,000 years ago, and you measure the bubble in that particular sample of ice core, which is 300,000 years old, and measure the methane and carbon dioxide concentration within that small air bubble, because now we have got very sensitive instruments so that even that small bubble is enough to measure. So you can measure the temperature profile at the time series for the greenhouse gases. They exactly mimic the temperature. So again, another convincing argument to suggest that there is a direct correlation between the temperature of the atmosphere and the carbon dioxide content in the greenhouse gas. Carbon dioxide and greenhouse gas concentration in the atmosphere. Now, about the different greenhouse gases, carbon dioxide is the dominant one, about 75%. Methane is less. Next, then nitrous oxide, and then there is this hydrofluorocarbon. These are the four principal. And this is about the lifetime of the greenhouse gases. You remember that there was this argument when Arrhenius pointed out first that the carbon dioxide can give rise to rise in temperature. The argument against that the carbon dioxide will be dissolved in the ocean. So now we have more accurate measurements, and we can determine how many years a gas stays in the atmosphere before it is removed from the atmosphere by surface processes, by solution in the ocean, or by reaction with the rocks and being absorbed in the rocks. So in this way, they are removed from the atmosphere over a geological period. So carbon dioxide, it is now found out that 50% of the carbon dioxide is removed over a time scale of 30 years. 30% more is removed in a few centuries, and the remaining 20% stays in the atmosphere for thousands of years. Water also is a very strong greenhouse gas because it absorbs quite a bit of infrared ray. But water has a very small lifetime, because very soon, whatever water vapor, additional water vapor is put in the atmosphere, within a few days, it will come back to the earth as precipitation. So it has got a very short period. So addition of water vapor is not of much interest for climate change scientists. It is the carbon dioxide which can stay over. If you put some carbon dioxide here, about 20% of it can stay for thousands of years, 30% of it will stay for hundreds of years, and 50% will stay for at least 30 years. The other gases, they stay for even more, like methane stays for 9 years. Nitrous oxide stays for 130 years. These halocarbons, chlorofluorocarbons, some stay for 10,000 years. So once you put the greenhouse gas in the atmosphere through your industrial activity, they remain in the atmosphere for a long time to come. Again, another point the scientists are interested in, that if we want ways to mitigate the effects of the carbon dioxide emission, we need a better knowledge of what type of activity is releasing what type of gas. So that if we know that, we can find out that where our corrective action should be focused. So that's why they measured up how much carbon dioxide or greenhouse gases are emitted by different human activities, different industries. So electricity and heat generation, that is 30% of greenhouse, responsible for 30% of emission. Transport, vehicle emission is for 15%. Manufacturing and construction material, cement industry, that is 10%. And the other activities, agriculture, land use change, etc., they are relatively small. So main is this electricity generation, transport, and industry. These are the main sectors of industrial activity which is responsible for the greenhouse gas emission. This is about India. Indian situation is slightly different. Here, 41, because here it is industrially less developed than the West. So it is towards slightly different. But here also we find that 41% is electricity, emission is due to electricity, 4% from other energy sectors. Apart from these thermal power stations, there are some other sectors that they also indirectly emit some carbon dioxide. 34% from industry, 5% from building, and 13% from transport, and 3% from agriculture. So this is slightly different from the global averages. The other type of activity, that is one way of changing the greenhouse gas in the atmosphere, industrial activity, human induced. The other one is other human activity which can cause this greenhouse gas emission is deforestation. Forests are important because forests absorb a lot of carbon dioxide from the atmosphere to build up their bodies, to build up the tree trunks. So they absorb the carbon dioxide from the atmosphere and make it less. So if we cut down the forest, then that absorption becomes less. In other words, that leads to indirect increase in the concentration of carbon dioxide. if we cut down the forest, if the forest was there and there was a certain amount of carbon dioxide, and then if the forest is cut down, the absorption will become less, so that the carbon dioxide concentration will relatively increase. And in addition to that loss of absorption, it also changes the albedo, because forests are dark. So they absorb, they do not reflect very much sunlight. So they absorb the sunlight. Whereas if we cut down the forest, it becomes a more light-colored, brownish, yellowish ground, which reflects the light. So that it reflects light and more light goes back to the sun. So this change in albedo is also a result of the deforestation. So from this, you see all the carbon, the greenhouse gases, the major greenhouse gases, carbon dioxide and methane, they have got carbon. Nitrous oxide is very little in concentration, but it does not have any carbon. But because the major contribution is from carbon dioxide and methane, nowadays it's a common practice to express instead of talking about carbon dioxide concentration and methane concentration, what is the total carbon content? So carbon dioxide translated into carbon. So here to build up the models for climate, I'll come to that later, they had just the idea of sources and sinks of carbon. So what are the sources of carbon from which we can put in the atmosphere? The sources are the fossil carbon, the fossil fuel, petroleum and coal, which we burn to produce carbon dioxide, and in other words, put carbon in the atmosphere, and from the deforestation. The carbon which is stored in the forest, if we cut it down and burn it, that carbon goes back to the atmosphere. So these are the two main sources, fossil carbon and land use change. And what are the sinks? Which absorbs the carbon dioxide from the atmosphere, so which mitigates the effect of carbon dioxide. One is the ocean sink, which is the ocean where water dissolves the carbon dioxide. One is the land sink, which like the forests, they absorb the carbon dioxide. And one is the atmosphere, that the atmosphere itself contains the carbon dioxide. So this is the source and this is the sinks. For carbon cycle it goes from the source to the sink, and then from the sink it goes to the source and comes back. So this is a cycle, we live this cycle. We come back to the aerosol, which is also produced by industrial activity. It is a fine suspension of fine solid particles or liquid droplets in a gas. The aerosols, they absorb and emit and reflect light. So if they absorb light, that will have a positive radiative forcing. And if they reflect light, that means it goes to the outer space, it will have a negative reflective light. So this has got some of the aerosols have got a cooling effect, some of the aerosols have got a heating effect. But overall, majority of the aerosols has an overall cooling effect, not heating like the greenhouse gases. Now we come to this. So these two effects are human. Now we come to the natural causes. Natural causes, carbon dioxides and methanes and nitrous oxide, these gases are emitted by the volcanoes, which is the natural emission, but they are relatively less important because a volcano whatever amount of greenhouse gas a volcano can emit in an eruption, 150 times more than that carbon dioxide is emitted by human activities. So volcanoes they have an effect, but that is very negligible compared to the human emission of carbon dioxide and methane. And then you remember that one radiative forcing was the change in the solar energy itself. The solar energy itself can be of two types. One is natural causes. This can be either the changes in the Earth's orbit. This change can be of three types. One is the eccentricity of the Earth's orbit. That means this is the Earth is at the center. This is the sun, and the Earth moves in a circle. And if its eccentricity changes, it becomes an ellipse, so that the Earth in this part comes closer to the sun. In this part, it goes from away from the sun. And in the over the thousands and millions of years, this eccentricity of the Earth has changed. The other is the tilt of the axis and the precession of the axis. Tilt is the Earth's rotation axis, and the angle of the rotation axis with the plane of the revolution. And the third is the precession. And these things, they are cyclic. So the eccentricity, it has a cycle of 100,000 years. Tilt has a cycle of 41,000 years. Precession is a cycle of 23,000 years. So these effect it will have an effect in the solar radiance. So this change in the solar radiance will be wavy in a time scales over thousands of years, not in 50 or hundreds years. It will be many thousand, tens of thousands of years. And then there is the sun's solar irradiance itself. The sun gets dimmer or brighter. We can see that there are some years where there is a lot of solar sunspot activity, where the sun is brighter, and when there is less sunspot activity, the sun is dimmer. And on a very small time scale, the sunspot activity is over a period of 11 years, and there are larger cycles of sunspot activity. So there are human causes and there are natural causes. But then how do we know that the observed climate change that we find, how much of it is due to the human activity and how much of this is due to the natural causes? The way to do that is through we model the weather. This comes from climate modeling, and we put various boundary conditions and work out the theoretical models of the climate and compare that with the observed climate. This is a very technical, and it needs a lot of computation. Basic mathematical formulations are simple. It is based on Newtonian mechanics, primarily on Newtonian mechanics and thermodynamics. But it has to deal with large volume of data and also a very large and complicated interactions between different factors. So till the modern computers came, we could not make or prepare effective models of the climate. So the other point to note here that any modeling of the climate it has got an effect called the butterfly effect. So what does a climate model do? Essentially, what it does is that it puts a boundary condition. Suppose we have a certain composition of the atmosphere and a certain initial thermal state of the atmosphere. Say we start with a composition with 5% carbon dioxide and at a temperature of 3 degrees centigrade. So we put a given amount of carbon dioxide additional and then work out how that a particular increase of carbon dioxide will change the energetics of the total atmosphere. It will change not only the temperature, but the temperature increase will affect the ocean, the land temperature, the ocean temperature. Ocean temperature will cause further evaporation. So all these interactions will have to be considered. And because these complex interactions are there, we start with the initial conditions, and then it is found, it is called a butterfly effect, that a very small variation in the initial condition eventually leads to a very large variation in the final condition. So this is known as a butterfly effect. Why butterfly effect? Because the idea was that there is a fluttering of butterfly in Brazil will cause a tornado in North America. This is as an anecdotal thing it came. So this slide shows that how our progress of modeling has started. The first models were simply dealt with emission of carbon dioxide and removal of water by rain. And then gradually more and more factors and interactions were put into place, and we got very sophisticated thermal climate models now. This is a subject by itself, and perhaps someone with climate modeling can have another discussion session on this climate, how this climate modeling is done. So first we start with we have measures of the radiative forcings, the values of the different factors which are important controlling factors for the climate. And we determine the radiative forcings and then work out the temperature distribution for a given amount of radiative forcing and have a model. This is the original initial temperature profile. This is the surface temperature, gradually decreases. This is the top of the atmosphere. And then in the stratosphere, it again starts increasing. So remember that the radiative forcing is that equilibrium condition is where this temperature profile is established. So if we add an extra energy from across the tropopause, that is the radiative forcing, which causes the disequilibrium, either more absorption within the atmosphere or less emission from the sun, less energy coming from the sun. So the additional energy comes at the tropopause, and then how the temperature profile changes. So these are different models that shows the temperature profile. So there are these ideas I will leave now, that they have to consider how the different factors, there are feedbacks, and there are positive feedbacks and negative feedbacks. And then there is, so if we get a very vicious circle for global warming. I'll just highlight only one aspect of it. One is that if you put increased carbon dioxide that will give rise to increased global warming. This increased global warming will increase the ocean temperature. This ocean temperature will give rise to will change the condition of the ocean phytoplankton and greater evaporation from the ocean. So there will be more carbon dioxide and more water going into the atmosphere. The more the temperature of the ocean increases, the more carbon dioxide and more water will go into the atmosphere. So it will increase the temperature more. So this has got like a feedback effect. So there are positive feedback, negative feedbacks, and then there is also a very important aspect known as the tipping points. Tipping points mean, this is also very important this is gained very importance in the current period now, that tipping points are some changes which are caused by this greenhouse gas concentration increase, that some changes take place which are reversible. That means if you take away the carbon dioxide from the atmosphere by some means, the effect will come back to its original position. So the ocean is heated, the ocean will come back to its old temperature. But there are some aspects which are irreversible. Like if we take the ocean temperature, if we increases beyond a certain limit, then the ocean circulation model changes. And then if you bring back the temperature again to the old temperature, the same circulation model of the ocean will not come back. So the tipping point has been exceeded. So this is a great worrying thing. And now the scientists are suggesting that with the global increase of 1 degree centigrade, we are very close to the tipping points of some aspects of our environment. So we are in a very dangerous situation now. Some tipping points will be exceeded soon. So this is that, and the impact of the climate change I will not discuss today. I think I have talked about more than an hour, I think. So this is about the main scientific things to establish that climate change is taking place, and to establish that the climate change is due to human activity. That part I will show you now. How to know what factor actually caused the past and which caused the human change. This is the red one, is the present day observed profile from 1850. And the gray one is the model temperature change due to natural causes only. Because we know all the solar changes, we know about all the volcanic eruptions, so we know how much, what is the quantitative effect of the solar irradiation change and quantitative effect of the volcanic eruptions. So we can change what would be the nature of the change due to natural causes. This is the curve. You can see that this gray curve is not coinciding with the red curve. So natural causes cannot explain the increase in temperature since the Industrial Revolution. So next is, we have calculated the models ignoring the natural causes, only the human-induced carbon emission. That also is measurable quantity. So we have measured that, and the gray thing here, and you can see that this thing is largely coinciding, but not exactly coinciding everywhere. So anthropogenic forcing also does not explain the entire phenomenon of climate change. But if we take natural and anthropogenic together, then the curve closely fits with the observed curve. The model curve closely fits with the observed curve. So this gives a confidence in our model, and it also suggests that whatever climate change we are observing is primarily due to human factor and minor due to natural factors. So this is the science is very clear about this part. And obviously, if we want to mitigate the effects of climate change, we must find out some means of taking out the carbon dioxide from the atmosphere and store it back in the sink. Now, how to do that, and what would be the effect of that? That is a separate subject altogether. That is more about the future prediction of the climate change and the what political activities or socio-economic activities we can take to bring about the mitigation of that climate change. That I will not discuss today, maybe some other day. So so much about how scientific aspects of the climate change and its positive factors of the climate change. The impact and the future ones may be discussed later. But if you have questions, I can answer. Or if you want to discuss the impact and the other part.
Okay, thank you, Professor Mukhopadyay. Now, if anybody has a question, then yeah.
So I have one question.
Yes.
I'm Jani Basha. Actually, why that some major temperature increase at North Pole and some cool spots are there in oceans? What is the reason for that? I want to understand.
That is observation. The part the greater increase in the North Polar Arctic region is primarily due to the feedback effect, because there is a large feedback in the change in the Arctic region, because Arctic region earlier was covered with ice. So this ice reflected back a lot of radiation back into the space. So the ice has dramatically melted over the period of the last 150 years. And because of the melting of the ice, it is now absorbing very much more radiation from the sun. So that causes more warming in that. These things can be, it is very difficult because it's as I mentioned again and again, this climate is a product of very complex interactions between many different physical, chemical, and also biological features. Not only human beings, but the metabolic activity of the animals and plants, that also affects the climate, because they also emit greenhouse gas or absorb greenhouse gas. So to these complex interactions, because of their great variability in the space, the climate change, there is an average warming of the earth as a whole, But because the different factors are not uniformly distributed over the surface of the globe, the temperature increase is not uniform over the entire surface of the globe. And this can be mathematically modeled. If you take a particular area, for example, if you take India, so you can model the climate for India. For that, you need measured data from India.
Yeah, there's a question in the chat box from Asif Alam. Please repeat that portion. What is the positive impact of climate change?
What is the
Positive impact of climate change. Positive impact.
not positive impact of climate change? I have not discussed at all about the impact of climate change. Positive and negative thing I discussed was about with reference to the role of the different factors which cause climate change. That is, some changes in the physicochemical conditions or biological conditions, they give rise to heating or more energy in the atmosphere. These are the positive changes, and some changes lead to cooling of the atmosphere. So these are the negative factors. For example, I may mention that carbon dioxide, this has a positive radiative forcing, because the presence of carbon dioxide absorbs more energy, so it absorbs the energy. Whereas the high reflecting surface, that has a negative effect, because high reflecting surface, if there is, like the Antarctic ice, it reflects the light back to the space instead of it getting absorbed by the Earth atmosphere system. So that has a negative radiative forcing. So we discuss positive, negative with respect to that, whether it leads to temperature rise or temperature fall.
Okay, thank you.
There
Another question.
I have not discussed at all what are the different impacts of climate change. That is a separate topic. I can discuss that. It will take about 10-15 more minutes. But let us have the questions first, and then if there is time, I can go into that.
Yeah, one more question in the chat. Is there a connection between the holes in ozone layer and global warming?
Ozone, as I mentioned in that, if you remember that diagram of the absorption bands, ozone is a greenhouse gas. So presence of ozone would increase, the increase in the concentration of ozone would have the same effect as the effect of increase in the carbon dioxide. But this is for the ozone in the atmosphere. Okay, but the main layer of ozone is not in the atmosphere. Atmosphere has got very little concentration of ozone. The main concentration of ozone is in the stratospheric region. And there, the ozone acts as an absorption of the ultraviolet ray from the sun. So that absorption by the ozone layer of the ultraviolet ray coming from the sun protects us, the life on the earth, from the harmful effects of ultraviolet radiation. Now, industrial activity, particularly related to refrigeration, that has led to the emission of some greenhouse gases known as hydrofluorocarbons. which break down the ozone. So these increased emission of fluorocarbons as a result of industrial activity has the effect of destroying a portion of the ozone layer in the stratosphere, which is called a ozone hole. A less constant ozone hole means it's not just a hole. It's not like a hole. It means that the ozone concentration there has decreased than it was before. So decrease in ozone concentration means we are more susceptible for the infiltration of ultraviolet ray from the sun to the surface.
Dhruba, we got 3 questions from YouTube. Shall I place them now?
Yes, one by one.
Yes. So the first question comes from Devarsi Gangaji. He says, how can we calculate temperature during 1850s? Is it carbon dating or something else?
No, temperature instrument, that was the first meteorological stations were established in the 1850s. So we have those meteorological data. They are thermometer measured data, weather station data. And fortunately, India also has some very old stations. We have also 1850 records. 1850, I think the earliest data in India is about 1858 or 1859.
Okay. So how do you also determine the temperature before 1850, for example?
Before 1815, I'll give you some examples. One is from tree rings, which is say can be measured for about say 700, 800 years, up to that range before today. That is from the tree rings means, if you see the very ancient trees, if you study a cross section of the trunk of a tree, you will find there are rings, and the rings are annual rings. So there are, if the annual rings, they have it's a dry season, wet season ring. These two together, the couple forms a ring. So each year, that is one ring with a couple. And by counting the number of the rings, you determine the age of the tree. So the outermost ring is today, that is recent. And the innermost ring is when the tree was first planted. So you determine the age from that. And the width of that ring is a measure of the temperature. The higher the temperature, the greater the width. So from that, you determine both the temperature as well as the year.
Okay.
But this tree ring is can be employed only up to 700, 800 years old trees. I think the oldest one is about 850 years or so. Then we can get from the isotopic ratios of oxygen and hydrogen in the small air bubbles within the iron ore, within the ice core. You can also determine the very tiny uranium concentration in the dust particles present in the ancient soil, ancient ice, and even sometimes in the ancient trees also, fossils, you get this dust, and you can measure the uranium also. So from that, you can determine the age. And the temperature you can determine from the ratios of the different isotopes, which are thermally controlled. Oxygen 18, oxygen 16 ratio, or carbon 12, carbon 13 ratio. or hydrogen 2, hydrogen 3 ratios, or deuterium hydrogen ratio. These ratios can tell you about the temperature of that.
Okay. Okay, the second question here is that the glacier, and this question is coming from Babu PS.
Just one point about this. But naturally, the error bar in these different measurements will be different. The instrumental record has got a very small error bar. Say within 0.1 degree you can measure. But if we measure from, say, isotopic ratio, that will be measured in a time span of, say, 100 years or 1,000 years. Okay, so this point you have to determine, and when you make a model of the climate, this relative accuracy of the different methods of measurement has to be an input in the model. So how you can put your temperature today and the temperature 800,000 years ago, and if you want to see how the temperature has evolved, your uncertainty at 800,000 level and your uncertainty at, say, 1880 is different, and that has to be incorporated in the model. So these refinements are getting more and more. So as our computing power gets more.
Okay. So Dhruba, I go to the next question, and it is coming from Babu PS. He says the glacial interglacial temperature difference is 6 degrees.
About 6 degrees.
About 6 degrees.
Temperature difference.
Yes.
But both are below zero.
Both are below zero. And present rise above mean temperature is hardly 2 degrees. Why would it not come within the glacial interglacial oscillation of temperatures?
Repeat that. Can you repeat that once more?
Yes. So let me read the entire question. It starts with saying the glacial interglacial temperature difference is 6 degrees, and present rise above mean temperature is hardly 2 degrees. Why would it not come within the glacial interglacial oscillation of temperature?
Glacial interglacial temperature is taking place over a period. See here the scale. This is the interglacial peak. This is the glacial bottom. See, the difference is, this is 350,000 years and this is 250,000 years, 100,000 years difference. And this today's temperature, see this, see how it is taking. It is as if this is happening in a second compared to hours here.
Okay, okay, that answers the
That
question.
is why this part of the change is very worrying, because we are causing changes at a rate which is unprecedented earlier. Not only the temperature value is important, but also the rate at which the temperature is increasing.
Okay, okay. So there are some more questions on our Zoom chat box. So maybe the person who is posing the question may unmute and place the question directly. Professor Thankachan.
Yeah, my question, including my suggestion, including my question, is we have to fix a time limit up to what time we can go, because we have to come to the political questions. So the science questions, how far we can take, we have to decide. So that that is applicable to my question also.
Can I reply?
Yeah, I was also worrying about this issue. Anyway, Dhruba, you want to say something?
Yes. You see the model, as we go further and further back, the uncertainty in the model becomes larger and larger. The climate modelers are very confident about the last 170 years from 1850 to here, because their model, they can model exactly the observed temperature change. Okay, so whatever future predictions you make, that should be based on the basis of models fitting the observed temperature curves from 1850 till today. And even more so during the last, say, 100 years or 150 years. If you see the temperature change earlier, the first curve which I showed, because that is the thing which is of importance, this one. You see, this is up to here, the temperature was increasing at a slower rate. It is only from 1970 afterwards that the temperature has increased at a steeper rate. This is because from 1970 there is more and more industrial activity and more burning of fossil fuels. It can be exactly compounded with your carbon consumption. We have data that how much carbon dioxide is coming. You can see that the carbon dioxide from industrial activity, it fits exactly with this curve. So it rises.
Probably the competence question was related to how long can we continue taking scientific questions, and then we need to go to discuss the political issues related to this.
Scientific questions is this much, that we can fairly, scientifically, it is absolutely well established that from the Industrial Revolution, there is temperature increase. From the Industrial Revolution, there is greenhouse gas concentration increase, and there is great probability that the increase in greenhouse gas is responsible for is the primary factor responsible for the observed increase in temperature. Now, on the basis of the climate models, which are best fits to the observed temperature, we can now build up future models that how much carbon dioxide we have to decrease from the atmosphere to lessen the effect of the temperature increase. Like if it is business as usual, if we don't do anything, go on doing as we are doing now, this curve will go on. Then that will be disastrous for human civilization. So it is, everybody agrees that if we want to have a more amenable condition of living, we must do something so that the temperature does not go on increasing continuously. That's why all this political discussion was that in the Paris conference, they decided that up to 1.5 degree increase in temperature from then, from the 214 or 13 level, up to 1.5 degree temperature is manageable. That means human beings and their civilizational, all the infrastructural things can be adapted to 1.5 degrees. 2.5 degrees, it will start becoming unmanageable. And beyond 3 degrees, it will be catastrophic for the human beings. So now we should, globally, we should take some measures so that the temperature does not increase beyond 1.5 degree. And to do that, we must have, now the modelers have precise ways of determining that what should be the carbon dioxide concentration at 2100 to have 1.5 degree increase at 2100. So there is 400 ppm of carbon now. So we know that, say, up to 460 ppm, if we can keep ours carbon dioxide condition, we can keep the temperature within 1.5 degree. So this is a different subject altogether. I have not discussed, but if you want, I can go on now and discuss those aspects.
No, actually, we need to go into discussing the political issues.
Not just the political, the science also in future.
Yes.
About the on
yes,
the basis
science,
of which
yeah.
science we have to decide the politics. So
Okay.
what the first part of the science we have discussed, warming and human-induced warming. Now what to do about it scientifically and what to do about it politically. This has to be decided. Now, what to be decided scientifically, we can discuss today, if you want.
Yes, if that is the precondition of discussing what to do politically, then that has to be taken up.
Yes, from breakthrough, we should proceed in that is the way we should proceed. That science, what does science tell us? What to do? And then what demands we make from the politics to obey that science. That is what organizations like Breakthrough or all scientists should say, that science wants politics to do this.
Okay, then let us go into that aspect. Let's finish that part of it.
I think we should have another session also.
Yes.
Besides today, yeah.
Yeah, I agree to that. I think that has to be discussed in detail.
We cannot, yeah.
Yeah, we cannot.
Already
Already
so well.
Today.
Yeah, oh, it has already been 2 hours. Yes.
Yeah, 2 hours. But I think if this part, I think I have been able to convince at least you that it is human-induced.
Okay, then if the political question is not taken out,
which is responsible for the climate change, and if we don't do anything, the temperature will go on rising. So if you want to prevent that, we should do something to lessen the concentration of greenhouse gas in the atmosphere.
Okay, Tankachan, you were saying something?
Okay, then I have placed one question in chat box. There was an article in the Hindu newspaper that is written by UN, that chairman of the that committee, UN that committee. I forgot the name. He says 1/3 of the emission is from meat industry, but the presentation showed that the agriculture or such activities had a minimal contribution to the emissions. So Dhruba, please comment. 1/3 of the emission come from the meat industry. That was.
You see, there is nothing for me to comment. This is what the data says. It is not any opinion. It is hard data. You see, this is the emission by sector in billion tons. This is from the electricity, this is from the transport, and this is from agriculture. This is from agriculture. Agriculture includes animal husbandry. This is of the order, in 2016, it is of the order of 10%. 10% of the GHG emission comes from agriculture. And 30% of the GHG emission comes from, this is globally. In India, it is slightly different. This is about India. The data are from 2018. Beyond 2018, data are not yet in the public domain. So in 2018, from electricity, it is 41% of the total emission, and agriculture is 3%.
Meat industry is also an industry, so maybe it is in relation to the industry.
Meat industry is not. It is included in the meat industry, in the agriculture. The factory itself, if there is any factory of like the canning of meat, that may go in the industry. But the raising of the livestock, because main methane emission comes from the livestock, cow fermentation, that is a source of methane.
Tangachan was talking about meat industry. There is meat processing. Meat processing industry.
Factory goes in the industry.
That is what he was referring to, not the meat industry, that is processing industry.
Does not produce very much methane. Methane, major part, is produced from agriculture, from rice fields, and from livestock. Main amount of methane comes from that. Main amount of methane does not come from meat. Main amount of methane comes from fermentation of cows going on in the enteric region of cows, not from the meat. From the meat, carbon dioxide is emitted.
Okay, anyway, I shall share that article. Then we can discuss more. One more question.
Yeah.
One more question. There is a widespread confusion regarding the role of methane. This wetlands and the agriculture also contribute to the contribute methane. So the presentation but shows the methanes that their life is compared to carbon dioxide less. So their contribution to the global warming is less.
No, not only that. Not only that. There are two things about methane. Methane is many times more potent than carbon dioxide. Okay. Methane is many times more potent. One molecule of carbon dioxide, if you take, and one molecule of methane, methane will absorb much more. I think it is 25 times more or 85 times more than one molecule of carbon dioxide. But overall, carbon dioxide is more total emission if you consider. Carbon dioxide is more important because the volume of carbon dioxide is very much more than methane. But in future, along with carbon dioxide, people are also emphasizing the ways to reduce the methane emission also. So that is for the future. But till now, till today, till 2022, the role of methane emission is subordinate to carbon dioxide emission. even though methane is more potent than carbon dioxide, but its total volume, total content of methane is much less, very much less, I think. And methane is also short-lived relative to carbon dioxide. That's why carbon dioxide also, for a long time planning, carbon dioxide is very important.
But the spectrum, the infrared spectrum, that diagram shows the contribution of methane is very less compared to carbon dioxide. Can you please show the that spectrum again?
This does not show the contribution, the how much it absorbs. It does not show the strength. It only shows that in this wavelength band, methane. This is the methane. It's with this wavelength band, the methane absorbs the infrared at this wavelength band, whereas carbon dioxide absorbs at this wavelength band. So what wavelength band you are sending, it will also depend on that. And this is the profile of the infrared which is emitted by the Earth. And this thing is being absorbed. So methane would absorb in this range, whereas carbon dioxide and water vapor will absorb in this range. You see, if this is the profile, the major part of the energy comes in this range, and this is the 2 sigma range. So methane's effect will be felt at this range, which is a small part of the infrared spectrum. Have I been able to explain myself?
Yes, yes.
Can we discuss now the impact of all this little more detail, the next part of?
Yeah, I think we have to organize another discussion because we have already been 2 hours. So
we'll have another discussion on the impact and future. Right. What science tells about the future.
Right. We need to organize another.
Yes.
In any case,
maybe even a couple more. A couple more.
Okay, let's see. We'll decide the timing and let everybody know when the next meeting will be held. But I would request everybody to, since this talk will be available, if any part is not understood, you can go back, listen to it, and when we meet the next time, we should be informed. I want to